well, I'm guesstimating about halfway through. Oh, there's somebody arrived. To get halfway through trig integration, there are lots and lots of different situations involving trig functions. And that's going to make your life quite difficult, because what that, for instance, means is that you only maybe get whatever examples I do, you're only likely to see maybe one more example of it. If you're really lucky, two, but that's about it. And that's not an awful lot of practice at every one of the different situations that are going to happen. So I strongly suggest that you go to the ebook and look up some more examples from section 7.2 and do those, and then look at the back of the book and see if you got the answers right. Otherwise, you're just going to see me do one example and then another different question, a different way of doing it, and so on and so forth. And you're really not going to be able to get the skills, the skill building that you need to be good at these. So I'm going to start with a single trig function. And I'm really only picking this for completeness sake. That one is a non-starter. By that I mean there's virtually nothing you need to do, because the answer is pretty obvious, right? Now we're going to look at how you would integrate okay, there's another person, this guy. There are going to be two main themes or strategies for doing trig integrals. One of them, you're going to use trig identities. What that will allow you to do is to turn the question from what it looks like into something else that you know how to integrate. And the second main theme is U-subs. And a lot of questions, you put both those together. Right? You do both things. You use identities, but you also use U-subs. So let's look at the U-sub here. Whenever you have a U-sub in these kinds of questions, it's always a single guy. It's either sine theta is your U-sub or cosine theta. You're not going to do cos cubes or sine squares. They just never turn out right, typically, right? So think single. Which one would be the U-sub in this question?
It doesn't matter.
It doesn't matter. So give me one. I don't care which one I use.
Sine.
Sine. It doesn't matter in this situation. If both powers are the same, you're going to end up doing pretty much the same amount of work if you use this as your U-sub or if you use cosine theta. Now, what will happen is that the answer will look quite different. When I use this one, the answer is going to have sine thetas and sine cube thetas and stuff like that in it. If I use cosine theta, it's going to have cosine thetas and cosine squares and cosine cubes in it. So you could end up with two totally different answers, both of which are equally correct. Why do you think I chose that one and not the other one? And it's a minor reason, but I chose it anyway.
There's no negative.
Yeah. If someone had given me the other one, I would have still picked it. But I was trying to give you the choice. I don't like negatives because, as you know, I'm careless. And isn't it easy to forget a negative or to lose it somewhere? Now, the crossover.
You know, you could call yourself an optimist if you just forget to be negative.
Megan, are you trying to be funny? God, that was bad. But it was so bad, I like it. That was cool. Did you just think of that?
Yeah.
Oh, okay. Well, you know, I've told you a million times to stop exaggerating.
Sorry, I'm muted. You just can't hear me laughing.
Okay. Kathy, did you get that one? Sam, I've told you a million times not to exaggerate.
Yeah, I don't get it.
God, a million times is ridiculous. It is an exaggeration.
Oh, okay, I get it.
Okay, let's continue with this process then. I've distracted myself and you lot enough. Sine cubed becomes u cubed. That's good. I would leave the cos cubed alone for a few moments. The d theta becomes this fella. And cancel out one of the cosines. And it's very, very common for something like this to happen. Now, normally you would be worried in a U sub if there was some thetas or cos squared thetas left over. But this is where identities kick in. I'm going to look at another way of writing cos squared theta. And if I go over here, do you see that I can write cos squared theta as 1 minus sine squared? See that? I could use it as this guy. This one is the one I'm going to use, and I'm not going to use that one. Why am I using this one and ignoring that one?
Because those are for double angles.
Yes. So, you didn't catch that? Because there's signs in it. And why are signs good? Because my U sub has signs. Which means that this question has now become that question. Are you happy about the fact of why I did this next line? Why that's not much use, but this is. Right? And that's very common as well in these questions. Power rule. Power rule. And remember to return. Now, if the question is an indefinite integral, you have a plus c. If you don't put the plus c in, WebAssign going to tell you you're wrong. On the other hand, if this was the integral from 0 to pi, then wouldn't this now become theta equals 0 to theta equals pi, and you plug in some numbers and you'd get, you know, whatever you got, right? 7/9 or something, or 0, or whatever. So if there are limits of integration, your final answer is going to be a number. If these are missing, your final answer is just going to be plus c. And it's easy to not notice that and do virtually the whole question correctly, but you haven't like finished it the way it needs to be finished off.
I have two questions real quick.
Yes.
So with your final answer, is it minus 1/6 sine of 5, sine to the 5th power theta?
Yes.
Or is it to the 6th power?
You all caught that deliberate mistake. It's a 6 power. And you had a second question.
I was curious to know if we would be able to use the sine of 2 theta identity, where it's equal to 2 sine of theta times cosine of theta, and divide by the 2 to have it.
Well, you'd end up with 1/8 the sine of 2 theta. Because it'd be a half, and a half. And could you do that? Yes, and it would work.
Okay.
Now, that was a sine and a cosine, both being odd. Here they are both odd. In this question, either method would work and both would be correct. In this question, either method would work, but for practical purposes, only one of those is the right use up. If you try the other one, it'll take you like 50 minutes, an hour to do it because it's ridiculously big. If you do the correct choice, it's relatively quick. What would be the correct use up?
Cosine.
Tell us why.
Because you immediately, when you put that u in there, knock out like 15 cosine.
Right.
You only have to deal with one minus cosine squared.
Yeah, exactly. Right. So I wouldn't do that, but what you said was bang on, right? Now, what happens if you do the same? Trust me, you are going to have the biggest looking polynomial in the world. It literally will be that big. And if you fight your way through, it is correct. And if you did it in an exam, well, that would be the end of the exam because it probably take you half the time you do it that way. But theoretically, at least you're correct. But in practice, when they're both odd, always pick the big one for your use up. Right, so that's us covered combinations of odd and odd, right? Let's do an odd and even combination. It is a use up. That's good. At least they're all use ups right now.
I would use the even one, so sine, because then we'll still have that 1 minus sine squared left over. Or, I mean,
No, I know what you mean. You're right.
yeah.
Yeah.
So that extra cosine cancels out. We have a 1 minus sine squared. Boom.
With the sound effects, boom. Here we go. du by d theta. Actually, since there's only two u subs in the world, couldn't you probably just write down what the final answer is because you're going to do lots of questions where it's a sine or a cosine. So if I do that, are you happy with me just going, you know, cut to the chase? That's going to be the guy at the end. So what do we have? Well, we're going to have a u to the 4, which is good. We're going to have a cos cubed theta, a 1 over cosine theta du, which is what that mess is saying. We have this fella. And this fella becomes 1 minus sine squared. And this fella becomes 1 minus u squared. Now, hopefully there'll come a point in time where you don't need every single one of those lines. That you can go from 2 to 4 or line 1 to 3 or whatever it is, right? You can skip a line here and skip a line there. Because they're a kind of same old, isn't there? The same kind of things happen over and over again. You get a little bit comfortable about skipping a step here and there because you kind of know what it's going to turn into. Would you agree that all I'm left with now is a power rule? And I'm going to dot that because you know how to finish those off. Well, you might say, what would happen if I picked the wrong one? What would have happened if I'd chosen cosine? Right? Well, you would have got rid of only one of the sines. So you would have been left with a sine cubed theta, a u cubed, and a du. Sine cubed thetas can't be turned into cosines only. Right? You won't be able to get rid of all of the sine cubed. That's why it's a problem. That's why it doesn't work. So if it's an odd and an even choice, your rule, if you want a rule, is pick the even one. So if it's sine to the 6th power of theta plus cosine to the 11th power of theta, pick the even power. Are we good? Now, let's show you a single odd pair. I don't think I've done that. Single odd pair, yeah. Checking. Yeah. Let's do a single odd power. Actually, let's make it harder. Make it 5. There. This isn't going to work for us. A U sub won't help me. Actually, it isn't the only U sub that's viable, sine theta, and that's not much use. So I know it's not going to really work. So I have to think of, what do you do when it's a single odd power? Well, you break it apart by sucking out only one sine, in which case I now have sine to the 4.
And then you can put that in terms of cosine and then use cosine as your sub, which would cancel out that extra odd sine theta.
Correct. So sine to the 4, sine squared squared.
So that's 1 minus cosine theta squared.
Yep. And then at this point, can't we do a U sub of cosine theta? And can you trust me, you end up with an awkward negative, which you just have to live with. And it's going to be 1 minus U squared squared du. Where would I go next with this fella? Because he's not really very, I don't like the way he's written as far as integration goes. What wish I have to do?
Distribute.
Okay. And that guy gets you -1. That guy eventually gets you 2 of these, and you get that fella. And then can't we dot, because we're pretty much broke the back of that one. Now that's what you're going to do with a sine cubed, a sine 5, a sine 7, also a cos cubed, a cosine 5, and a cosine 7. So this is what you do when it's a single odd power. But that's not what we're going to do with the next situation. What do you do when it's a single even power, like sine squared, for example? Any ideas before we move on and I tell you? So we're here.
Oh, would you use that 1/2 1 minus cosine 2 theta?
You would. So you would use this identity. See, we found a use for it. Then distribute the half. So in this question, there are no U subs. I don't need a U sub. Well, I guess you could do a U sub in 2 theta, but don't we have a shortcut for that? Right, the linear one. So this fellow would get you half theta. If you do a cosine, you get a positive sign. So that negative cosine gets me a negative half sine. That 2 gets me an extra half. So at the end of the day, you get that guy. Are we good? If I had time, I'd go over more permutations of evens, but I only have time for one last one. What do you do if they're both even?
Rewrite
Ch-
it and then take the integral.
Chris, you're a bit quiet, so I'm not sure if it's your mic needs to be turned up. So what were you suggesting? I can't hear you at all now.
If we break one of them into the trig identity, then you can cancel out.
Ooh, I'm under sure. Well, what trig identity are you thinking about over here, I'm assuming, right? Which one of these are you wanting to, well, which one are you going to use and which one of these is it going to turn into? I guess that's what I'm asking.
Well, like if you do sine squared theta and turn that into 1 minus cosine squared theta.
And that would generate eventually a cos squared theta, take away a cos to the 4th power of theta, right?
Yeah.
That adds possibilities. But what would you do with the cosine to the 4th power of theta? Yeah, it's a bit hard now, isn't it? I mean, it's doable, but I guess I could call it this guy and square this guy. Do you see it's kind of growing like a monster, bigger and bigger and messier and messier? That would eventually work, but I wouldn't want to do it that way just because it would be horrendously long. But as a strategy, it would work. I'm going to look at this guy differently. Sam, you actually touched on this.
Are you going to look at it as 2 sine theta cosine theta squared over whatever that would end up being? Because I guess it would be over 4.
Right, Sam, you're nodding. Is that what you were thinking?
Yeah, pretty much.
Okay, so I'm going to take it just a little bit slower. Because if you try and do too much, especially if it's novel and I've never seen it before, the missing lines are the things that will kill you. Right, would you agree that all I've done here is basically rewrite sine squared cos squared as a single sine theta cosine theta being squared? Do you agree they're essentially the same, right? Now, this guy here is pretty close to what I have. The problem is he has a 2 here. Now, if this was 2 of these, I'd get sine theta. But since he's not, can you see that you get a half the sine of 2 theta? Are you happy about the quarter that Megan was talking about? This is where it's coming from. Isn't a half of sine 2 theta this guy? Think of what a half of this would be. Wouldn't it be a sine theta cosine? Now, if you FOIL it out now, you're looking at that guy. And it's good, and it's kind of bad. The good news is that it's a little bit nicer than it was. The bad news is, how do you integrate sine squared 2 theta? And it's not that obvious what you should do. But this is the only thing that will work. We have to figure out another way to write that guy. Now you're going to go over here and say, but there aren't any sine 2 thetas, and there definitely ain't any sine squared 2 thetas. Nonetheless, I am going to use this guy here. But I'm not going to think of that theta as being a fixed thing. I'm going to think of that theta as a placeholder where you can put anything you like in. And so it's sine squared, whatever you put here, is going to be a half, 1 takeaway cosine of twice whatever you put here. And if I put 2 theta here, wouldn't that end up being 4 theta? You see that? Sine squared 2 theta, 2 lots of 2, 4 theta. So 1/4 of a half, 1 takeaway the cosine of 4 theta. That other method that you suggested earlier, you'd end up having to do a very similar thing, but you'd have to do it to like 3 different things. So it's like 3 times as long. What do you think I should do next?
distribute.
So that gets me an eighth. Take away an eighth. And we are good to go. Right, I don't need to do any U subs here. This guy is 1/8 theta. And this guy, well, if you integrate a cosine, you get a sine. Because it's 4 theta, you get an extra quarter. So that's where the 32 comes from with my C. Do you see the different tweaks and techniques for just combinations of sines and cosines? Just downright, you know. And I haven't covered every possible, you know, nuance, but at least we've got the main tricks of the trade. Before I move this, is this one okay? Are we cool with this one? Right. Next fella in the road then. We are going to look at what happens when you have combinations of sine and cosines and the other guys. Now, who are the other guys? The other guys are basically secants and tans, right? So I'm going to do a sine with a cosine, whatever it is. Yeah. This one happens to be a version of question 8. So we're going to look at the integral of the 6th power of tan cosine x, let's see what I've got here, of 7th vela, that guy. Just so we don't get too caught up with thetas, you know, x's and t's are also allowed. So what you need to do if you ever see tans and sines, tans and cosines, secants and sines, secants and cosines, right? One guy from here meeting up with one guy from here, right? That kind of combination. You can approach these the same way. What do you think my first step's going to be?
Convert tangent into sine over cosine.
Yeah. Turn everybody in sight into sines over cosine, because we are good at dealing with sines and cosines, right? We're not very good at dealing with tans and secants because they're just weird, right? But sines and cosines we're much more comfortable. Isn't the tan a sine over a cosine? So won't a 6th tan be the sine of 6 over the cosine of 6 times cosine of 7x? Now, after you do that, you typically are going to cancel things out, right? Make them pretty, see what happens. A lot of good stuff's happening here. Doesn't that kill off most of that? And now I'm going to be left with this fella. Agreed? How am I going to solve the problem now?
U sub sine.
Yeah. Haven't we already covered that? If it's an odd and an even, isn't the U sub the even guy? Right. Can you just trust me? You get U to the 6 and then ... and you're finished. Are we good? Oops. I want to do a very similar . I'm just going to make this cube and I'm going to make this squared. Hopefully I get this right. Yeah. Turn them into sines and cosines. This time when you cancel, do you see that there's a cosine left on the bottom? That's new, because that could happen, right? Although it's new, it's not going to use a new technique. It's going to use a U-sub. Who's the U-sub going to be now?
Cosine.
Great. Why did you pick that? Agreed. Agreed. So here we go. So I'm going to have a rather ugly sine cubed, right, over a u times a negative 1 over sine x du. That gets me negative 1 over u with a sine squared x left over, right? And we know how to tackle sine squareds, don't we call them 1 minus cos squareds? Sine squared, 1 minus cos squared.
So then you end up with negative 1 minus u over u, or u squared.
Right, so you end up with this guy, right? Negative 1 over u, this guy. Distribute. You happy about that times that and that times that? This guy is a half u squared. What about negative 1 over u? What's that going to look like? Antiderivative. Negative 1 over u.
Negative natural log of u.
Finished.
Don't you have to replace the u still, though?
Oh, darn it. Well caught. And I could imagine me being really pleased with myself and then cursing WebAssign for saying, why is that wrong? When, well, I'm 90% right, but I'm not 100% right either. Yes. Well caught. Do you see the variation in things that could happen and how you have to adjust and adapt? A little change like 1 power being a little bit different from the other, didn't it kind of go its own little world a little bit different because of that? Sometimes the smallest change can make a big difference in the method that you use to solve it. Let's just look at a single tan. None too scary. A single tan. How am I going to find its antiderivative?
U sub for cosine.
So the assumption that I'm making is that you've already realized that it's that guy, and therefore you use a U sub. In this case, I believe you get negative 1 over sine x du equals dx. Can I skip the middleman now because we've done so many of those damn things? That's going to get me a negative, well, let's do it in order. It's going to get me a sine x over a u times a negative 1 over sine x du. That ends up being this fella. And that ends up being natural log of u. And that becomes this fella. Hey, we now know what the antiderivative of tan x is. It's negative the natural log of cosine x. But that isn't, although it's right, it's not the way it's written. How does negative the log of cosine become the log of a secant?
You can take out the exponent from the cosine inside the natural log. So that's how they get the negative. So if you like put it back where it was, then it'd be 1 over cosine x.
Right? That's where it came from. Trig is full of little nasty, sneaky, dirty tweaks that will kill you. If Weber's being really nice to you, won't negative log cosine x plus c be fine? But if it's going to be nitpicky and lawyer-esque on you, don't you have to know it's the log of the of a secant? So don't automatically assume that your answer is wrong. Think, is there another way I could write this darn thing that would make the computer happy? Technically speaking, isn't the natural log of a secant slightly, and I'm talking about a micro-inch slightly, better looking than the negative log of a cosine? You're pushing the envelope there a little bit, aren't you? You know, you're being really nitpicky now. There are lots of times where I wouldn't argue with it. You know, if you have a big horrible mess, but it can become a really nice looking pretty thing, right? That would be definitely more advisable. Before I forget, will you all take your attendance right now? Say hi. And while you're doing that, do you know I'm just telling you what the integral of secant x is? It is provable, but we're not going to get into the ugly math. Can you just assume that that's now a standard integral? In fact, since we've just found out what it is,
Can't see what you wrote.
oh, I'm just squeezing in the tan guy at the bottom. This might seem like I'm going backwards, but there is a reason for what I'm doing. What's the derivative of secant x? What do you get if you differentiate?
Secant x tangent x.
Agreed? If you turn that on its head, then does it not mean that the integral of a secant tan is a secant? Agreed? What's the integral of secant squared? It's a standard integral that we haven't used much. So it's just a matter of memory. It's a tangent. Now, the reason I'm doing these two guys and these two guys is that we're about to start looking at integrals that have tans in them and secants now, right? We've kind of covered sines and cosines in all their flavors, right? And we did a little bit of sines and tans or sines and secants, right? We haven't done any sines and secants, but it'd be the same kind of question, right? And now we're going to focus on what do you do when it's only secants and tans? And there is quite a big overlap. In other words, you do very similar things, right? So For instance, this is example number 9. This is in fact the last question for today. Let's look at combinations of tans and secants. In this case, an odd power of tan x, and a secant cubed of x. When you get a combination that looks like this, it's also a u sub. And the rules for u sub are the same as for sines and cosines. You only pick a single guy. So the u sub is tan x, or that u sub is secant x. In some situations, both work, but not this one. Who is the u sub for this particular one?
Secant x.
Correct. Now, if you differentiate with respect to x, remind you again, what's the derivative of secant x?
Secant x, tangent x.
Right, I put it here. Can you see why I did that now? Why I just brought that back? Because it's going to be a derivative that's going to happen at least half the time, right? Now, that means 1 over secant x tan x du is what dx is, right? I kind of skipped a line there. So let's see what we... Yes.
So when you do your u sub, you would still leave one of those secant x's out, so you can divide the tan x secant x away, right?
Yes, you're about to see me do exactly that. So yep, you are right. Normally, you would immediately turn that into u cubed. I suggest very strongly that you don't do anything to it yet. In other words, in these tan secant questions, have this line where everything stays put and just turn the dx into that. Now, when you do that, what you were getting at, it makes perfect sense now. Do you see how the tans cancel and one of the secants cancel? Now that leaves me with 4 secant squared x du, and secant squared becomes u squared.
Then you get to do the power rule and put secant x back in.
Does that feel good, guys? So it's not 100% quite like a sine cosine. In a sine cosine world, can't you tell all the guys into use right away and it's not an issue? But in the secant tan world, don't you have to hold on just for a little while? Right, just leave them alone. Because there's if I turned that into a u cube, couldn't you see, oh God, I'm left with a thing and what the heck am I going to do with this bit? It's left over, and you know, you could go down a road that confuses you. Whereas if you just leave it for a minute, let it sort itself out and then say, okay, I'm ready. Boom, boom. Now, I know that was the last question, but I have a few things. Can we pretend that we did a similar question, right? And that the similar question is that this was a tan cubed, right? So what happened here is that you only killed off one of the tans. So now I'm going to be looking at 4 secant squared x, and there's going to be a tan squared x left over, right? And u was secant x. Well, the secants are good. I have a tan squared to deal with. It's a bit like, you know how you have a sine squared left over and you have to make it cosines? Kind of like that. What will a tan squared become?
Secant squared theta minus 1.
Right. You see I'm
X,
using this guy?
yeah.
With x's.
Yeah.
So this tan squared becomes secant squared x take away 1, which now becomes u squared take away 1. Multiply the whole thing out. And basically dot, 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 right? So the technique that we've shown you here is how to take care of an odd secant and an odd tangent, right? Like a tan cubed, secant cubed, a tan x, secant cubed, right? Actually, it will work for a tan cubed secant squared. It would also work in that situation. Right? So how do I know that this is the right u sub? If the tangent is odd. Use that guy. So if you're doing a combination of powers of secant and powers of tangents, the rule's quite different, right, from what you do with sines and cosines. The rule is, if the tan is an odd power, use secant. Does that make sense? So if it's tan to the 5 secant squared, tan to the 5 secant cubed, tan to the 5 secant 149, you're still going to use secant in every one of them because the tan 5 thing. Right? So next time we're going to look at, well, what do you do when it's an even power of tans, right? Like, what do you do if it's a tan squared? Yeah, you know, a tan to the 4. But what's that phrase? You've got to keep your audience wanting more. So I'm going to leave you at this point, hoping that you want to find out how to deal with even powers of tan, right? Because if we can fix that, we're pretty much finished this section, right? And that'll give us a good head start for next week. Okay, is there any questions? Is everybody happy? Well, bye-bye, guys. I shall see you, oh God, tomorrow.